Many professionals assume educational outcomes are simply the result of what happens inside a classroom, an improvised real-time dynamic between a teacher and a student. That localized interaction is called teaching design. It is a micro-level strategy encompassing the individual lesson plan, the environmental setup, and the specific delivery executed by one teacher in one room. But zooming out reveals that this localized classroom execution is actually dependent on a much larger, invisible structural framework. This overarching architecture is instructional design. It is a macro-level collaborative engineering process that maps out complete educational systems, encompassing entire curriculums, resources, and training protocols before anyone steps foot in a classroom. Confusing these two tiers places an immense engineering burden on the teacher. This structural friction often results in inconsistent outcomes, as even the most skilled educators struggle when they are forced to invent the framework while simultaneously delivering the content. Building this macro system requires a multidisciplinary team. It relies on a designer, a subject matter expert, an evaluator, and the teacher. The subject matter expert guarantees the factual precision of the raw content. They ensure the material is accurate, comprehensive, and up-to-date. The designer takes that raw, verified content and structures it. They map the information into sequential, procedural pathways that the human brain can process and retain. Effective education relies on a predictable, engineered system designed to control learning outcomes. Achieving scalable, reliable learning requires removing chance from the equation. We build a strict, multi-stage engineering pipeline to ensure the material succeeds regardless of the specific classroom environment. This diagram outlines the engineering pipeline, which operates in 5 distinct phases: analysis, design, development, implementation, and evaluation. The transition between analyzing the environment and designing the actual educational blueprints is where most curricula break down. The design phase operates as a predictive science. By planning the instructional treatments, organizing objectives, and plotting evaluation criteria upfront, we eliminate downstream errors. This rigorous upfront planning drastically reduces the cognitive load on the teacher during the implementation phase. They are no longer forced to invent the structure, they only have to execute it. When a classroom consistently underperforms, the flaw rarely originates with the teacher's implementation. The failure traces back to a breakdown in the upfront macro design. To build an effective design, we first measure entry behavior. This is the mandatory baseline assessment of a learner's pre-existing skills, cognitive capacity, and developmental state before instruction begins. Once we know the starting point, we apply task analysis. This deconstructs major, abstract educational goals into specific, requisite subtasks. This map illustrates the logic of teaching division. Division is the top-level goal, resting on subnodes of multiplication, subtraction, and addition. A student cannot process division without first establishing the entry behaviors of addition and subtraction. When confirmed, the pathway to division activates, ensuring a positive transfer of learning, where past knowledge accelerates the acquisition of new knowledge, depends entirely on this strict sequential mastery. Misaligning a student's entry behavior with the task analysis guarantees instructional friction. The student faces cognitive overload, and the material becomes impossible to absorb. Performance objectives translate these tasks into action. A viable objective must address a real psychological or intellectual deficit, filling a gap to restore the learner's cognitive equilibrium. The difficulty of the objective must precisely match the learner's intelligence and motivational level. Set it too high and they disengage out of frustration. Set it too low and they disengage out of boredom. These objectives require exact, observable verbs. Using Bloom's taxonomy, designers distinguish between lower-order cognitive operations, like listing facts, and higher-order operations, like analyzing concepts. An objective must account for physical realities. A flawlessly written objective demanding typing proficiency is invalid if the classroom lacks a keyboard or typewriter. To measure these exact behavioral outcomes, we use criterion reference tests. These are precise data-gathering instruments calibrated to test the specific objectives rather than general aptitude. By rigorously constructing the performance objective upfront, the designer simultaneously dictates the correct instructional strategy and the exact metric used to evaluate success. With objectives set, content must be sequenced. Instructional technologists index and structure curriculum data like a massive library, ensuring information can be retrieved on demand. They rely on 4 primary sequencing architectures to build this cognitive map. This specific linear timeline accurately illustrates the forward chaining sequence. This method is deployed when steps must strictly follow a chronological or physical execution path, moving predictably from the easiest initial step to the final outcome. This alternate sequence demonstrates backward chaining. Here, the final objective illuminates first, and the learner steps backward through the prerequisites. This approach provides a distinct psychological advantage. By making the ultimate goal visible and tangible from day one, it generates immediate motivation and context for the learner. This pyramid structure represents the hierarchical sequence, championed by theorists like Gagne and Merrill. Hierarchical structures force the brain to move from specific foundational components at the base, synthesizing them upward into complex general wholes at the peak. Finally, this macro map visualization shows the elaboration sequence developed by Rylith. This sequence establishes a broad, comprehensive macro overview, the epitome, before drilling down into high-resolution micro details. Selecting the wrong sequencing architecture for a specific subject matter prevents the brain from organizing the information, breaking the learner's ability to index and retrieve that knowledge later. The entire design remains theoretical until the evaluator steps in to close the instructional design loop. This relies on formative evaluation. Unlike an end-of-course summative grade, formative evaluation is the real-time iterative testing of the system itself while it is being built and implemented. We visualize this process using metrics like those established by Dick and Carey. The evaluator actively stress tests the instructional network. They target the nodes with uncompromising questions. Was the instruction engaging? Did the tests measure the stated objectives? Was the learner feedback sufficient? Without this rigorous, ongoing formative feedback, a massive curriculum investment is merely an untested hypothesis. Continuous evaluation loops provide the scientific data required to guarantee the curriculum adapts to the reality of human cognitive friction, isolating failures in the material before they reach the student. There is a common professional anxiety that applying macro-level engineering and strict protocols to education stifles classroom creativity. Rigorous instructional design eliminates structural and cognitive friction. Clearing these systemic obstacles allows the educator to focus entirely on human interaction and inspiration. A flawlessly engineered curriculum is exactly what frees the educator. Pedagogical freedom occurs when a teacher can step into a classroom and focus on instruction, operating with the confidence that the underlying curriculum architecture is mathematically and psychologically sound. Comprehensive design elevates the teacher from an isolated curriculum improviser to a precision operator of a successful system.